Let's continue our discussion next with this example. Here we see three functions f, g and h. All of them are functions from the set of natural numbers into itself, and we are defining these functions by these formulas. F of x is 2x, g of x is 3x plus 4 and h of x is sin x. We have to show that h composition g composition f equals h composition g composition f, or in other words, that in this specific case for these specific functions, function composition is associative. And what that means is simply that no matter how you bracket this composition of these three functions, you get the same function. Now, instead of showing this for this specific example only, let us see that actually it's a consequence of a general theorem. In general, function composition behaves like this. So that is what we are going to see next. So this is that general theorem. Here also you see three functions f, g and h, but now the sets involved are arbitrary sets. F maps x into y, g maps y into z and h maps z into s. And these are just any functions. Then for these also that same thing is true. H composition g composition f equals h composition g composition f. Let us now prove this. The proof starts by noting that both these functions, this one and this one, have x as their common domain and s as their common codomain. Let's see how. Let's first take this one, which means we have to first of all figure out what type of function g composition f is, and then only we can think of the entire thing which has three functions. What does g composition f do? G composition f takes us from x to z via y by the definition of composition. How is that? Well, you take any element of x, say a, small a say. What does g composition f of a mean? It means that you apply f to a first, getting f of a, and then you apply g to f of a, getting g of f of a. That's what this composition means. So you start your journey in x at a, at the element a, then you apply f to that and you get f of a, which is an element in y. On that you apply g, and it makes sense also because y is the domain of g, and you get g of f of a, which lies here. So that's how you go from x to z via y. That's why we write g composition f maps x into z, and we use this to draw another conclusion. I mean, we write the sentence like this: since g composition f maps x into z, that is why h composition g composition f maps x into s. Why? Well, we can extend our argument. So g composition f takes you from x to z, and whatever you are getting here, on that if you further apply h, and you can, because that thing lies in z and z is the domain of h, then that gets you to s. That's why ultimately you end up in s, starting your journey in x somewhere, say at the element a. That's why this really is a mapping from x into s. It has x as its domain and s as its codomain. Next, let us consider this one. What about this one? Here we have this composition, this inner one, h composition g. Now, just like we argued right now and figured out that g composition f maps x into z, what can we say about h composition g? H composition g means we are applying g first to whatever input there is, and then on that result we are applying h. So that will take us from y to s via z. G will take us from y to z, and then h will take us from z to s. So that way h composition G maps y into s via z. And what does f do? F, you already know what f does. F maps x into y. So now you think of this composition. F first takes you from x to y, and then h composition G then further takes you from y to s. So again you are starting your journey in x and ending your journey in s. That means this also, this one maps x into s. That is, both this as well as this have domain x and codomain s. So now, having known this fact, now we can ask whether they are equal as mappings, and that amounts to showing that they produce the same output for a given input coming from x. So that's what we are going to next show, and that is rather easy. So we take any element x in x, the common domain of these two functions, and say apply this on x. H composition G composition f of x. By the definition of this composition, which you have to consider first because it is the outer one, this equals h of this of x, h of G composition f of x. However, the meaning of G composition f itself is this, G of f of x. But h of G of something means h composition G of that thing, which that thing here is f of x. But then this of f of x means this composition f of x. So you see that yes, both the functions are producing the same output for a given input x coming from the common domain. So that is why as functions they are equal. And you can write your conclusion like this. Hence, this function is equal to this function, and that is the proof. Next, let us see this example where we have two concrete functions f and g. F maps the set consisting of 1, 2 and 3 into the set consisting of the letters a, b and c, and g maps a, b, c into this other set having the three objects apple, ball and cat, and the functions are defined by these formulas. F of 1 is a, f of 2 is b and f of 3 is c, and g of a is apple, g of b is ball and g of c is cat. We have to show that f, g and their composition are all invertible, and the inverse of the composition is equal to the composition of the individual inverses, but the order has changed. Instead of having g first followed by f, here we have f inverse and then g inverse. Now this is what we are going to do about this example. We will create actual inverses for the functions f and g, showing that they are invertible. But then what about the rest? It turns out that these are general facts, that whenever f and g are invertible, then their composition is also automatically invertible, not just for these two functions but in general. And this equation is also in general true. So we will show that f and g are invertible for this example, and then we will prove the rest in a general theorem. Instead of writing a full solution, I will only give you hint in which I will define those functions which are potential inverses of f and g. And I define f1 like this. I am calling it f1, you can call it anything you want. From the set ABC to the set 1 to 3, recall that f maps 1 to 3 into ABC. So the inverse should be like this, and I define the inverse like this. f1 of A is 1, f1 of B is 2 and f1 of C is 3. What does f do? F maps 1 to A, 2 to B and 3 to C. This map does the exact opposite. It maps A to 1, B to 2 and C to 3. So what you have to do is you have to prove that this F1 really is the inverse of F. How do you do that? Well, you go back to the definition of inverse. You have to form the compositions of F1 and F, the two possible compositions, F1 composition F and F composition F1. Both have to be identity functions of the relevant set. That's what you have to show. And the one for G is this one. Let me call it G1. From the set apple, ball, cat to the set ABC. And G1 is defined like this. G1 of apple is A, G1 of ball is B and G1 of cat is C. The original G did what? It mapped A onto apple, B onto ball and C onto cat, and this does the exact opposite. And I have written it here. Show that F1 is the inverse of F and G1 is the inverse of G. And now let's go to that theorem which tells us the general fact which is the rest of this exercise. Example, sorry, not exercise. And this is that result. What does this theorem say? Say f is a function from x into y and g is the function from y into z, so that you can think of this composition G composition F, that it makes sense, and it will of course be a function from x into z. So if these two functions are invertible, then their composition is also invertible and its inverse is this thing. Let us now prove this. Just like the proof of the previous theorem, here also we first of all make sure that both these functions, this one and this one, have the same domain and same codomain, because then only next comes the question of them giving us the same output for a given input, and then they will be equal as functions. So first we figure out the domain and codomain. What is f? F maps x into y. So f inverse will map y into x, because that's what inverse does. So we note that down. G maps y into z, so G inverse will map z into y. Alright. So now what will F inverse composition G inverse do? This composition will have the domain of G inverse as its domain, because that's where the function calculation starts. You first apply G inverse to the input. So the input must come from the domain of G inverse. The domain of G inverse is Z. Okay? And then whatever you get, on that you apply F inverse. And then after that, where will you be? You will be in the codomain of F inverse. That means X. So this maps Z into X. So this much is clear. What about this function? That's the inverse of G composition F. What type of function is G composition F itself? G composition F maps X into Z, because F first takes us from X to Y and then G takes us from Y to Z. So this takes us from X to Z. So its inverse will do the opposite. It will take us from Z into X. So you see that both this one and this one map Z into X, Z into X. Both of them have the common domain Z and common codomain X. Alright. So now we can do the next part. Okay, so in this next part, we have to prove what? Actually, our aim is to prove that G composition F is invertible. That means it has an inverse. And we are guessing that that inverse is this. F inverse composition G inverse. To prove this, we have to show that this composition of G composition F and F inverse composition G inverse is the identity function on Z. Why do we say so? Well, that is because what type of function is this entire composition? This one maps z into x. This one, not the inverse, okay, only this one maps x into z. So we start in z and come back to z if we follow this composition. And now if we can prove that this composition actually is just the identity map on z, that means whatever you start with, you get that back, then that is one half of showing that this is the inverse of this. The other half will consist of interchanging the positions of these two. That means this one comes first, followed by this one. And we have to prove that that composition, which is a function from x into x, is the identity function on x. If we manage to show these two things, then that will not only prove that G composition F is invertible, but actually it will show that this itself is the inverse of G composition F. That's what we are doing here. So to show that this is the identity function on Z, we take any element from Z, say small z, and then apply it on Z. If you apply the maps one after another, which is actually how you should do it, you have to write many steps. Instead, I wrote the final step after applying all the things successively. First, I applied G inverse on Z, then to that I applied F inverse, then F, and then G. Okay. Now, what can you say about F and F inverse? We already know that F is invertible with its inverse F inverse. So, F composition F inverse is identity function. It does not change anything. What is that anything here? That anything is G inverse of Z. So they together, they nullify each other's effects, and they do not change G inverse of Z. So they vanish and we just have G inverse of Z. The same argument you apply to G and G inverse and you get Z. That's what we wanted to get, right? It shows that this entire function does not change any element of Z. So this really is the identity function on Z. Now next we have to show that other thing. So next we take any element x in X and we consider this composition, this time starting with F inverse composition G inverse and composing that with G composition F. And we are applying that on X, and like that you have this one, F inverse of G inverse of G of F of X. Again, just like F and F inverse just killed each other, these two also vanish and you are left with F inverse of F of X, and then they also vanish and you just have X. So this composition is the identity map on the set X, and that is why by the definition of invertibility, G composition F is invertible and its inverse is this one, F inverse composition G inverse, or in the form of an equation the statement looks like this: the inverse of G composition F is F inverse composition G inverse. Next we have this example. Consider the set S consisting of the natural numbers 1, 2 and 3, and we have used S to define 3 functions. We have to say whether each one of them is invertible, and in case it is invertible we have to find the inverse, and these are the functions written in set form. Set form means, you understand what it means. This one maps 1 onto 1, 2 onto 2 and 3 onto 3. This next one maps 1 to 2, 2 to 1 and 3 to 1. And this third one maps 1 to 3, 3 to 2 and 2 to 1. And of course, the explanation is already given in the book. So I leave the reading of this thing to you, and I want you to figure out what the book is saying. But if you still have any doubt, you let me know in the comment section below and we can discuss. But if of course there is nothing, no doubt is there, then we can from the next video start solving the exercises.